Hello my friends, and here we go with the implementation of a new method of our agent class, which will be the act method that will select an action based on a given state and a certain epsilon value for an epsilon greedy action selection policy. So here we go. Let's start by defining this new act method, which will take as arguments, well, first self for the object, but then since it will select an action based on a given state, well, it will take, of course, the state. And then also, since we're going to do an epsilon greedy action selection policy, well, it's going to take, of course, epsilon as the last argument. And we're going to give it a default value, which will be 0 point to make it a float. And here we go. Now let's define that act method. All right, so first what we have to do is start from the state, because right now at this point the state is a numpy array and we need to make sure it is a torch tensor so that we can work with the neural networks later on. So what we're going to do is call this function we know already from the torch library, which is of course the from numpy function, right? And which will take the state as input, so far a numpy array, but which will be converted into a torch tensor. Then we're going to make sure to set the data type as a float. And then we're going to do something else that we haven't done before, but which is extremely important for any deep Qlearning, deep reinforcement learning that you're doing. We need to add here an extra dimension to our state vector. Right now, we have 8 dimensions of the states, corresponding to the coordinates of the spaceship, the velocity vector, and etc. But we need to add an extra dimension which will correspond to the batch, meaning that this extra dimension will say which batch this state belongs to. All right, because we're going to work with mini batches. Instead of learning on one observation, we're going to learn on 100 observations. And so we need to know for each state in which batch it belongs. All right, and so that's exactly what we're about to do now. And the way we're going to do this is with a dot and then adding unsqueeze, then parenthesis, and then in the parenthesis you're going to have to enter the index of which you want this dimension of the batch to be. And since we usually put the dimension of the batch at the beginning, before the other dimensions of the state, well, we're going to enter here 0. So that the first dimension of our new state vector, but now torch tensor, will be at the beginning. Okay? So then we're just going to add 2 parenthesis self dot device, just to move it to the designated device, GPU or CPU. Perfect. And so, since all this actually updates the value of the state variable, well, we're going to add here state equals all this, so that now our state is updated to be a torch tensor set as a float with this extra dimension of the batch added and sent to the designated device. So that's perfect. Now, next step. Well, because we're about to forward pass the state through the local Q network to get the action values, well, we're first going to set our local Q network to evaluation mode. And the way we're going to do that is by taking first our local Q network and then add a dot and then call the eval function. So where does this eval function come from? Well, that's because remember, local Q network was created as an instance of the network class. And remember, the network class actually inherits from the, let's go back to part 2, it inherits from the module class by the NN module. And so we can use now the tool of the module class by the NN module, and one of these tools is of course the eval method to set our local Q network in evaluation mode. So let's go back here, there we go. Now thanks to this eval method we are in evaluation mode, and now we can forward path the state through our local Q network to get the action values. And how we're going to do that? Well, first we're going to make another check to make sure we're not in training mode, but in inference mode, meaning that we're doing predictions. And so to do this, we're going to add torch to call the torch library. And then from the torch library, we're going to call the no_grad function, which will make sure that any gradient computation is disabled. All right, then you're going to add a colon, and then just below, well, there we go. We're going to do something very exciting now. We're going to finally make the predictions from our local Q network to get the action values. And how we're going to do that? Well, first, let's introduce a new variable, a new local variable, which we're going to call action values, which will be, of course, the actions predicted, with the Q values. And how we're going to get them? Well, we're going to call, of course, our local Q network while entering as input, of course, the state. And that's exactly how you forward pass the state to the output layer through our two fully connected layers to get the final action values. But in fact, you're getting the Q values corresponding to the actions. And then you'll see we'll use that epsilon greedy policy to select the final action. All right, so let's do this. Now, since we're done with the inference mode by, getting those action Q values prediction, well, we're going to go back into training mode. And the way we're going to do this is, of course, by first calling our local Q network. And then again, just like the eval function, since local Q network is an instance of our agent class and the agent class inherits from the module class by the NN module, well, we're going to use another tool of that NN module, which is this time the train method. And that's exactly what sets our local Q network back to training mode. So great, now we're back to training mode as opposed to inference mode, making predictions. And so now is the time to do that epsilon greedy action selection policy. And so how we're going to do that? Let me remind you how epsilon greedy action selection works. So basically we generate a random number, and then we're going to say if this random number is larger than epsilon, the epsilon we set here, then we're going to select the action with the highest Q value. And else, if our random number generated is lower than epsilon, then we're just going to select a random action. And so, since I just explained to you what is epsilon greedy action selection policy, well, I'll try to press pause on the video and try to implement this if condition yourself to select that final action based on this epsilon greedy action selection policy. But now I'm going to do it with you. Here we go. So we're going to start with if, and then let's generate first this random number by calling first the random library, from which we're going to call this time the random function, right? We have first the library and then the function. And so we're going to check that if this random number generated is larger than epsilon, then what are we going to do? Well, we're going to do, of course, we're going to select the action with the highest Q value. And so, well, directly we can return that action with the highest Q value. And how we're going to do that? We're going to use a tool from NumPy, which is the argmax function, and which will allow us to do exactly what we want, meaning select that action that has the highest Q value based on the action values we already got here. Okay, so let's do this. We call NumPy first, and then from NumPy we call this argmax function, which will take as input, of course, our action values. But then, since this selection is a simple operation, we're going to send that to the CPU. And then, because the argmax function actually expects a NumPy format of data, well, we're just going to add here .data.numpy with some parentheses. And there we go. That will exactly select this action with the highest Q value. All right, good. And now we're going to do the else, meaning if the random number generated is lower than epsilon, then what are we going to do? Well, we're going to just select a random action. And so the way to do this is very simple. We're going to return a random action by using the choice function by the random library. So here we go. I'm calling the random library first, from which I'm calling this choice function. And then the trick, to select a random action among our 4 actions, which remember are 0, 1, 2, or 3. Well, the trick to do that is just to use NumPy and then this function from NumPy called arrange. And then inside, we just have to specify the action size, meaning 4. In other words, we're going to select a random index among 0, 1, 2, and 3, because 4 is excluded. Okay, so that will exactly select a random number between 0, 1, 2, and 3. Alright, so that's perfect, and we're done with this new act method that will select an action based on an epsilon greedy action selection policy. Perfect! So now we're gonna move on to the next step, implementing that new method, which will be the learn method finally, which will of course update the agent's Q values based on our sampled experiences. I can't wait to do that with you in the next tutorial, and until then, enjoy AI. Hello my friends and welcome to this new tutorial, a very exciting one because finally we're going to implement that learn method of the agent class that will update the agent's Q values based on sampled experiences. So it's quite a big method, so let's get started. We're going to define this learn method, which will take of course as argument self for the object, then our sampled experiences, and then the discount factor gamma, or if you want you can call this gamma. Alright, then colon, and here we go. So let's scroll down here to give some space, and the first thing we're going to do now is unpack our sampled experiences into their respective categories, meaning states, next states, actions, rewards, and dones. So here we go. We're going to create these new local variables here, which are going to be the states the next states, the actions, the rewards, and dones. And according to you, what are they going to be equal to? Well, of course, our experiences, because our experiences are exactly the tuples of these elements. All right, so we're just basically now separating, unpacking the experiences into the different elements: states, next states, actions, rewards, and dones. Okay, good. Now next step. The next step now is to get the maximum predicted Q values for the next states from the target network. And why is that? That's because then, remember, we're going to compute the Q targets for the current states, which include those maximum predicted Q values in the formula. So let me show you. First, let's get these maximum predicted Q values for the next states, which we're going to call next Q targets. Okay. And how we're going to compute them? Well, of course, we're going to use our target Q network, right? As opposed to the local one. Remember, we created with the constructor method in it here, we created our target Q network as an instance of the network class. So what I'm going to do now is take this and just below, I'm going to paste it here, because the first thing we're going to do now is forward propagate the next state from our target Q network. All right, good. And now what does this give us? Well, this gives us the action values of our target Q network propagating the next state. And therefore now, since we want to take the maximum of those action values, well, we're going to use the max function to get that maximum. But before, we actually have to detach the action values in the tensor in order to then get the maximum of them. So the detach function actually detaches the resulting tensor from the computation graph, meaning that we won't be tracking gradients for this tensor during the backward propagation. And then in this max function, we have to input a 1 here because we need the maximum value along dimension 1, which corresponds indeed to the action dimension in the tensor. But then it's not over. We also need to add here a square bracket 0, because actually after getting max 1, we get two tensors, a tensor of maximum values and a tensor of indices corresponding to the actions for these maximum values. And therefore, we need to add this 0 in the square brackets here to select just the maximum Q values tensor. But then actually what we'll have to do next is to add a dot on squeeze of again index 1, because we'll need to add again the dimension of the batch, but this time we'll add it at position 1. Alright, and that gets us the maximum predicted Q values for the next states from the target network, not the local network. And now that we have that, the next Q targets, well, we can compute the Q targets for our current state. And so let's call them Q targets, just like that. And it's going to be, of course, the reward plus the discount factor gamma multiplied by our next Q targets multiplied by 1 minus dones. Alright, that's exactly the formula giving us the Q targets for the current state. Make sure to remember that formula. You will implement it many other times. Okay, awesome. So now, next step is to get the expected Q values from the local Q network this time. Okay, so this time we're going to forward propagate the state from our local Q network, as opposed to propagating the next state from our target Q network as we just did. So let's do this. Let's call these new expected Q values Q expected. Okay. And then, as we just said, well, we're going to forward propagate the states from our local Q network. And therefore, let's just take it here. We're going to take our self.local Q network, copy it, paste it right below, and we're going to enter the state to indeed forward propagate the states to get the expected Q values from the local Q network. Okay, but then we're just going to add here gather, because we're going to gather all the respected Q values returned by our local Q network. And so how we're going to do this, we're just going to add 1 and then actions here in this gather function. Alright, so now that we have our Q targets and our expected Q values, well, finally we can get the loss, meaning we can compute the loss between the expected Q values and the target Q values. And therefore, that's exactly going to be our next step here. We're going to create a new local variable, which we're going to call, of course, loss, and which will be exactly that loss between the expected and the target Q values. And so, how are we going to compute that loss? Well, we're going to call our functional module, which we gave the shortcut f, from which we're going to call a new function, which is the MSC loss function, computing the mean squared error loss between actual values and predicted values, here respectively Q expected and Q targets. So here we go, let's call this function MSE underscore loss, computing the mean squared error loss between, and that's exactly what we have to input here in the argument, between first Q expected and then of course Q targets. Perfect, so now we have the loss, and so now according to you, what are we going to do? Well, of course, we're going to backpropagate this loss in order to update the model parameters to then update the new Q values, leading to a better action selection policy. Okay, so let's do this. That's going to be our next step here. But first, we're just going to initialize the optimizer by zeroing out the gradients of that optimizer. Basically, we're going to do a reset. And the way to do this is by, of course, taking another object we created in the constructor method, which is, of course, self.optimizer. So I'm taking it here, and then back below, I'm going to paste it right here. And well, to reset it, I'm going to call the 0_grad method. All right, because optimizer was created as an instance of the Adam optimizer class. Therefore, it contains this 0_grad method as a tool. Okay, good. And now, finally, time for backpropagation. We're going to backpropagate the loss that we just computed to compute the gradient of that loss with respect to the model parameters. So let's do this. It's super easy. We're going to take our loss that we just computed here, and then we're going to add a dot and then call the backward function. And that's it. That's all we need to do to backpropagate this loss. Okay? And that computes at the same time the gradient of the loss with respect to the model parameters. Okay, great. Now, next step. The next step is to now perform a single optimization step to update the parameters of the model. And so how are we going to do that? Well, we're going to, I think I still have it copied. We're going to take our self.optimizer, there we go, from which this time we're going to call the step method. And that is a method that exactly performs a single optimization step to update the model parameters. Okay, perfect. And now, final step. The final step is to update this time the target network's parameters with those of the local network, just like in deep Qlearning. And so how are we going to do that? Well, unfortunately, we can't do everything of it now. So what we're going to do is we're going to call the last method of this agent class, which we're going to create in the next tutorial, that will exactly do this update. And we're going to call it soft update. The soft update method, which will take as arguments our self.local Q network as the first argument. Then, of course, our self.target Q network. And then finally, can you guess? When we do the soft update, we always use the interpolation parameter. And that's exactly going to be our next and final argument here. Perfect, so I'll see you in the next tutorial to implement that soft update method, and until then, enjoy AI.